Hey everyone, today I'm here to talk about LLM Supply Chain Security. So let me give you an example. In 2023, a malicious package on PyPI compromised thousands of PyTorch installations, stealing AWS credentials and environment variables. And in the same way, in 2024, backdoor models appeared on Hugging Face, exploiting pickle vulnerabilities for remote code execution. The LLM supply chain is under attack, and today we are going to secure it. So, welcome to LLM Supply Chain Security. So, it consists S bombs, model cards, and AI bombs. So, let's get started. Let's start with the basics. Traditional software as a supply chain, code dependencies, build, deploy, and all. But LLM pipelines are far more complex. What we have data collection, model training, fine tuning, evaluation, and deployment. And at every single stage, there are attack vectors. How we can say is the poison training data can inject backdoors that compromise dependencies can steal the credentials. So, modified model weights can execute arbitrary code and then malicious plugins can exfiltrate the user data. The attack surface is massive. Here comes the real world threats. So, these are not hypothetical threats. Let me tell you what's already happened. Okay, in last December 2022, Torch Triton package appeared on PyPip. A typo squatting attack on the official PyTorch dependency. Anyone who accidentally installed it had their environment variables and AWS credentials stolen. So that's dependency confusion in action. And then throughout the 2024, security researchers found multiple malicious models on Hugging Face that exploited Python's pickle format. It means when you loaded these models, they executed arbitrary code on your system. That means remote code execution from just loading a model file. And it's not just attacks, we have supply chain weaknesses everywhere. How do you know your training data wasn't poisoned? And how do you verify that model weights haven't been tampered with? And then how do you track with the dependencies which were used during the training? So, for all these questions, here's the answer. So, this is why we need supply chain security for AI. And that starts with knowledge exactly what's in your AI system. And which brings us to software bills and materials. So, yeah, what is SBOM? So this is a software bill of materials is like an ingredient list of software. So basically it tells you every component that exists inside an application including the package names, version numbers, license, dependencies and even the supplier information. This is an extremely important for security because if a vulnerability is found in a package, you need to quickly identify whether that package exists in your system or not. So there are standardized formats for SBOM such as SPDX, Cyclone, DX, and SWIT, which makes it easy to automate the scanning and compliance workflows. So in short, we can say what is SBOM is. So this SBOMs provides visibility and you can protect which you can see. Next one is AI bomb. So we can say this AI bomb is an extension of SBOM for machine learning. Traditional SBOMs only track libraries, but in AI systems, the models and datasets are just as critical. So, an AI bomb records the model architecture. Let's say the weights file used, the datasets and their resources, preprocessing steps, evaluation metrics, and even provenance and lineage information. So, this helps organizations to understand how exactly a model was built and whether it is trustworthy or not. So the standards are still emerging, and Cyclone DX is leading development of ML bomb extensions. So we can say the SBOMs gives us the software transparency, and the second version of that, which is called AI bomb, that gives us a model transparency. This is the only thing in the AI bomb. Next, I'll show you the code practically where we generated the SBOM. So let me walk you through this slide now. So basically here we are generating SBOMs automatically. So for that we are using Swift to scan the Python environment to extract the dependency information, and then we use grep to scan those components are known for vulnerabilities like CVEs, and finally we use Cyclone DX tooling to format the SBOM so that it can be shared with compilers or any other security tools. So this result is a machine readable like JSON or XML SBOM that provides the full insights into what the environment contains. So this can be integrated into CI/CD pipelines to continuously monitor the security risks. So yeah, let me walk you through the code. First, let's generate a traditional SBOM for a Python project. An SBOM is a complete inventory of all software components, every package version dependency. Think it's an ingredient list of our software, yeah, as I said. So here we are using Cyclone DX, which is one of the standard SBOM formats along with the SBDX. So Cyclone DX is particularly good for security use cases because it includes the vulnerability tracking. So let me run this and show you the output. So after running, it will gonna scan our Python environment, like finding every installed package. Yeah, you can see the Swift is running. That is used to scan the current directory and to generate a response SBOM that is in the format of JSON. So then we will be converting that output into a Cyclone DX format. Yeah, you can see over there after running it's writing the SBOM JSON format response and then converting it into a Cyclone DX format. You can see the JSON file in the artifacts. Yeah. So as I said, the JSON is a SBOM. Basically, it's a machine readable, which means we can plug it into a vulnerability scanners, compliance tools, or security dashboards. So right now, it's focused on software dependencies like packages like torch, transformers, and so on. But for ML systems, we also care about the models and datasets. That's why where the AI bombs comes in. So next, let me go with the AI bomb. So it lets us register models with their structure and architecture, like as I said, the data sets and resources, license size, and all. So now we have a SBOM for a sentimental analysis model. We can see the model details, its architecture, framework, version, and the data set it was trained on, including the source and size and all. And let me run this. Yeah, there you can see combined with the SBOM, this gives us full visibility, like adding ML models, training data set, dependencies, and all. So next we'll use that SBOM to actually check the vulnerabilities. That is the next part. So once we have an SBOM, we can scan it for known vulnerabilities. So for this vulnerability scanning, we are using a Grape. That's an open source vulnerability scanner. So this Grape takes a Cyclone DX as bomb that reads every component and then checks it against the vulnerability datasets like CV and the GitHub security advisories. Sorry. And next, after, yeah, let me run this and let me show you the output of this. And yeah, yeah. So here we can see a list of vulnerabilities grouped by package. So basically each finding tells the package name, ID and severity which version fix it. So the power of S bombs, like you can fix if you can see, but here we can't fix like what we can't see. So the S bomb gives us visibility and the scanner gives as actionability. Next, we'll move from what we are running to what we can trust the model itself using the cryptographic signatures and provenance. This provenance answers a simple but critical question like, you know, can we trust this model? It represents the full history of the model, like who trained it, what data was used when it was created and all, like how it may have been modified over the time. So this provenance ensures the traceability throughout the entire ML life cycle. So this is especially an important and in the regulated environments and in distributed AI workflows, whereas models are shared between the teams and organizations. So the frameworks are like SLSA in Tattoo, Six Store, are being adapted to establish an end-to-end trust in this provenance. So let me walk you through the code. So first we generate an RSA key pair. We were using 4096 bit of keys for strong security. So the private key stays secret and this is what we use to sign. So the public key is distributed. This is what everyone uses to verify. So let me show you the output. So yeah, yes. So here in the output, you can see the keys are generated. Now here's the critical part. Because the private key must be protected in production, you'd store this in a hardware security model or a secrets manager. Never in a source code. That's the one thing. And to sign a model, we compute this SHA-256 hash, a cryptographic fingerprint of the file. Then we sign that hash with a private key. The signature proves two things: the model come, you know, from where it came from us, and it has been modified. So this is the two thing we need to take it. And next, on the other side of the signing, we are moving to the verification part. This is one more side of signing, that is verification. Before you load any model into production, you need to verify its signature first. That this is your last line of defense against the tempered models in our demo. The verification happens in three steps. First, we recompute the model's hash. Let me run this and show you. And the second is we compare it to the hash in the signature file, and if it doesn't match, the model has been modified and stop right there. And then if hash matches, that is a good sign. Now we need to verify the cryptographic signature using the public key. This signature verifies the model is authentic and it came from a trusted source and it hasn't been tampered with, safe to deploy. So yeah, if the verification fails when the ashes got mismatches, the system catches the tampering and refers that the model refuses to load the model, and this is exactly what we want, like the tampering detection before the model ever reaches to the production. And the third method is generating attestation. So here the signature proves the integrity but not the provenance. Attestations prove lineage. They don't document the entire history of how the model was created. We are using the in Turo framework and SLSA specifications here. So this is a signed statement about the build process. It records who built the model, when, and with what data, and using which dependencies. Think of it as a derived receipt of the model. And the material selection is crucial in this method. It lists every input to the training process and the data set with its hash. Let me run this and show you how the output attestation file is going to generate it. So this is machine readable and cryptographically signed. You can verify it or audit it and use it to reproduce the model if needed. So this is a fully supply chain transparency. So now we have the complete picture of S-bombs tells us what's in the model. Signature proves it hasn't been tampered with, and the attestations document, you can see the link which is providing. There you can see the pronouns. Yeah, like the attestation documents like how it was created, but there's a one more piece like human readable transparency to the model codes. That's the one good thing here. Yeah, so moving on to the next, model cards. So these model cards provide an human readable transparency. So like they explain what the model does, where it excels and where it may fail. They document things like performance matrices, intended use cases, bias in training data, limitations, and you know ethical considerations. While SBOMs and attestations are designed for machines and auditors, the model cards are designed for users, stakeholders, and we can say for governance teams, and to ensure the responsible deployments. It's just a critical part of explainable and accountable AI. So let me walk you through the code wise. So yeah, here I'm generating a model card for a bird sentiment classifier. I capture the architecture and version. Yeah, you can see over there. So that architecture and version intended the use cases like out of scope uses, data sources, and limitations. So this is the model card we generate automatically. That is the thing what we can do with this file. And let me show you the output. Yeah. So it documents the model's purpose, data, performance, and limitations in a way humans can easily read. So as you can see in the output, it's like it documented everything: the model architecture, version, and what it should not be used for, training, data sources, and any pre-processing. Like considering the bias and fairness and craves supports the limitations. This model code gets published alongside the model, and even using this model can read exactly what it's designed for. And yeah, so here you can see the response what it has generated. Like as I said, the output file which is saved in the name of bird sentiment classifier with all the version like JSON, readme, and YML file. There will be a output which is saved. So it's like a transparency and responsible AI in patience. So next, moving on to the next one, that is secure MLOps. So now let's pull it all together. It's a complete secure MLOps pipeline that integrates every security control we have discussed so far. So it's like a four phases, each with security controls. During training, we verify the data provenance, scan dependencies, generate AI bomb, and create model cards. So yeah, after running this, let me show you the output. So this is basically, as I said, during signing and cryptographically sign method and generate provenance attestations. During distribution, we publish everything to a registry. And yeah, this provides links to where we can navigate, like the dependencies link. So what the security checks happening at every stage, like the data verified, dependency scanned, AI bomb generated, model signed, attested, created, we publish to the registry, signature verified before deployment. This is a defense in depth of for an AI systems. So every security event is logged. This creates an audit, trial, compliance, and incident response. If something goes wrong, you know exactly what happened when. So yeah. So this is all about the coding part of the whole defenses and the signatures method. So yeah, yeah, as you can see the event where it's logged and when. Yes. So here you can see the security audit, the output file generated, which is in the JSON format. Yeah. Yeah. So you can see the each timestamp, what the action happened, and the details of that completely in this JSON file. Like as I said, every event which is logged. So yeah, this is complete coding part. So let's recap what we have built. We have implemented SBOMs to track every software component and AI bombs to track ML specific artifacts like models and datasets. So, vulnerability scanning to catch known security issues, and then next moving to the cryptographic signing to ensure the model integrity, and then provenance attestations to the documents, the complete build process, and the model costs for transparency, and the responsible AI. So here's your security controls like automate SBOM generate in your CI/CD pipeline and dependencies. Example, cryptographic keys verify signatures before every deployment. Scan for the vulnerability continuously. So create model cards for every protection in the model and track provenance from training through the deployment. So yeah, the LLM supply chain is complex, but it is not unsecurable. With the right tools and processes, you can build a trustworthy AI systems. All the code from today's demo in the GitHub repository, so you can clone it and run it, adopt it from your organization. So the threats are real actually, but are the defenses securing your LLM supply chain before the attackers exploit it? It's a very good way to implement in your systems. And lastly, thanks for being patient to listen all the LLM supply chain demo. And yeah, implement this and stay secure.